Hello everyone, welcome back to the lecture on drone systems and control. In the last lecture we have gone through A star algorithm and we have seen that how it can be used for global path planning. However, we were mentioning about some limitations. We will have a recap on those limitations again on A star algorithm, and this lecture the main focus is on RRT and RRT star algorithms for global path planning. So, the objective of this lecture is somewhat like this. We will understand what is sampling based path planning in high dimensional or complex environments. When we are talking about A star algorithm, it was not a sampling based path planning, but it was a grid based path planning, right. So, we will try to see that what are the limitations associated and then how it can be avoided by RRT or RRT star. Okay. So, in this lecture we will explain the core principles of RRT algorithm, which the full form is rapidly exploding random tree algorithm. Okay. Then we will describe the improvements introduced in RRT star for optimal path planning. Okay. Then we will apply RRT and RRT star to environments with obstacle and interpret the resulting paths. We will see that how things are happening over there, and then we will compare RRT and RRT star algorithm in terms of performance, path length, convergence behavior and so on. Okay. So, with that we will start the main contents of today's lecture. So, we will just have a recap on the limitations of A star algorithm. We have seen that for grid based path planning like A star, it is required to discretize the environment into nodes and edges before the path planning begins. That means, we have the map and then the total environment that is available in the configuration space will be discretized, right. So, the performance degrades in high dimensional or large search spaces because of these. Since before the planning begins, we have to discretize the environment. So, the memory expenditure in this particular thing is getting high, may expand many unnecessary nodes in complex environments. So, it becomes memory intensive as well. Okay. Another thing, another very important thing which we have noticed in A star algorithm is that it was performing well than Dijkstra algorithm because we included the heuristic function. But A star algorithm heavily depends on the heuristic function, and if it is not designed or tuned properly, then the A star algorithm may not give good solutions, right. So, it heavily depends on the quality of the heuristic function or the nature what we are choosing for the particular problem. Okay. So, it computes a single path once based on a fixed map. That is also very important, because what happens when an obstacle appears after planning, A star will not react unless there is a rerun from the scratch. So, we have to rerun the algorithm, recompute the path, and then only we will get another solution when the obstacle is coming into picture after the planning. Okay. So, it is not well suited for highly dynamic and continuous time systems without modification. Once we know that, now we will get shifted our ideas from A star to RRT. And okay, so what we see here is that in summary we see that the major problems with A star algorithm is that it is grid based search dependent algorithm. A star operates in discretized grid or graph. In high dimensional or continuous spaces, grid resolution must be extremely fine for accuracy, but that increases the memory requirement and certain other associated problems. Okay. So, this leads to exponential growth of search space. So, memory explosion will be there, and sometimes the computational time finally which we will be achieving is infeasible, right. Another problem is heuristic dependency. So, these are the two major problems of A star algorithm. Now, what is happening in RRT? It is a sampling based path planning algorithm which work incrementally and probabilistically. That means, the major difference is that it is not a grid based planning. So, we do not have to discretize the entire configuration space beforehand. Rather, this sampling based path planning can handle the situation incrementally and probabilistically. Okay. So, it forms a connected acyclic graph or tree rooted at the initial state where the robot or drone is at the initial position. Then it builds a space filling tree by randomly sampling the configuration space and connecting each new point to the nearest node in the existing tree. Okay. So, that is what RRT does. We will see it in more details. So, it is a kind of exploration driven growth, explores the free space using random samples, right. Okay. It is efficient in highly dimensional and dynamic spaces, high dimensional and dynamic spaces. It is fast and easy to implement for drones compared to A-star algorithm, right. So, how RRT helps? It is continuous state space handling. Since we know that we do not have to do it beforehand, and when some obstacle appears in the environment, then we do not have to rerun. So, in that way it becomes continuous state space handling. RRT works directly in continuous dynamic space, avoiding full discretization, and it efficiently handles high dimensional planning problems. Okay. Because when we get shifted from A-star to RRT, in that way we see that unnecessary nodes will not be created, and that will give the advantage in this particular way. Okay. The memory exploration can be avoided, right. So, no heuristic required. That is also a very important point, because tuning the heuristic in a proper way or in a required fashion is not easy all the time. So, if we can remove the heuristic dependency, then that is great for us. So, it is exploration, this exploration is driven by random sampling and heuristic guidance is not required. It is robust in unknown or dynamic environments where heuristic design is actually impractical. Okay. And it is better for scalability. So, it scales better in high dimensions by expanding only relevant parts of the space. So, we do not need to consider the entire configuration space, then discretize it, not required. Okay. So, it avoids evaluating the entire state space like A-star. Okay. If we want to contrast RRT directly with A-star, then we see that RRT uses random sampling, as we have told already. In that place, what A-star is doing? A-star algorithm searches over a predefined discrete grid or graph, becomes inefficient or infeasible in high dimensional spaces due to state explosion or memory explosion. So, for this particular thing, the requirement of memory will be very high, right. Okay. The second point is that it builds a tree incrementally, that is also very important. This incrementally by extending towards random points, avoiding reliance on discrete grids, that we have seen, which A-star is doing opposite. It actually this search is constrained to fixed graph nodes and edges, and incremental growth is not there. Okay. Then RRT can handle complex motion constraints, non-holonomic and kinodynamic constraints can be added, unlike A-star. Okay. Now, also RRT helps, it requires no explicit state space discretization, reducing computational explosion, already mentioned, where A-star needs the entire space to be discretized upfront, and there will be some combinatorial explosion. So, the memory requirement is getting higher. That is a problem for high dimensional scenario. At the same time, there is a that will be a problem for dynamic environments, right. Okay. So, RRT adapts well to dynamic and unstructured environments without full replanning. As I told that in a dynamic environment, suddenly if one obstacle appears, then A-star we need to run from the scratch, right, because what path it has given, it has fully computed the path with the discretization of entire configuration space. But since in RRT this thing happen or the explosion happen incrementally, so this particular thing can be handled, right. So, these features help RRT overcome A-star limitations in complex and continuous planning problems. Okay. So, in RRT, as we have seen, it is a sampling based exploration of configuration space, right. It is fast and probabilistically complete. What does that mean? If the path exists, then RRT is guaranteed to find it with maybe infinite number of samples or at infinite time, okay. But it will be able to find a path, that is guaranteed. Whether it is good whether it is useful or not, whether there can be any further improvement, that we will see later. But yeah, that guarantee we can give that if the path exists, RRT algorithm will find it out. Okay? Fine. Now, this tree expansion, what is happening incrementally is a greedy expansion. That is also something which we have to carefully note here, because it extends the tree with nearest node. Okay. So, many other things, other considerations or optimizations are not there directly, rather it is going inside the problem and finding the tree in a greedy way. Okay. It is good for kinodynamic planning with constraints that I have told, which is a clear contrast with a star algorithm. No guarantee of optimality. So, what I was telling here, it comes directly that no guarantee of optimality can be claimed here in terms of shortest or smoothest path. Okay. For that we might need some different improvement in the RRT algorithm, which will be coming at the later half of this lecture. Okay. Okay. Another thing is that the path may be jagged or long, and it is useful for real time applications when compared to, more useful when compared to a star algorithm. Okay. How RRT works? It is designed for continuous high degree of freedom systems like robotic arms, drones in 3D. It works in unstructured environment without grid discretization. Efficient exploration of large, complex or unknown spaces can be handled here, and it naturally handles complex obstacle shapes via sampling. Okay. Fine. So, we will see that what are the steps involved in RRT algorithm. Okay. So, first sample a random point in space. Okay. Now, find the nearest node in the tree to the random point. Okay. Now, what it does? It extends the tree from the nearest node towards the sample point, from here towards the sample point, that means here, fine, towards the sample point by a fixed step. Okay. And then it checks the collision. If the path from the nearest node to the new node, that means x near to x rand, is free of obstacles, sorry, x new is here, is free of obstacles, then add the new node to the tree. Okay. Then it repeats until the goal is reached, or you hit a stopping criterion by previously setting up that till what point you will run the iterations. Okay. However, there is a comment, the path generated is not guaranteed to be shortest possible path, because that kind of activity or optimization is not there inside the steps. Okay. So, each new node is always connected to its nearest existing node in the tree, but while doing that, whether it is a part of the shortest path or not is not being checked. So, the optimization criteria are not being included here. Okay. Fine. So, what do we see here? Sample the random point x rand in the configuration space, which is mentioned as C free, denoted as C free. Now, it finds the nearest node x near in the tree, okay, in the existing tree towards x rand, okay, to create a new node x new. Okay. If the x new is valid, what does that mean? That means the x new should not be outside the configuration space, it should be inside the set, right. So, if x new is valid, that means it is inside configuration space and it is collision free, that means going towards that point is collision free, then what happens? This x new will be added to the tree. Okay. These steps will be repeated until the goal is reached or the time runs out. Okay. Fine. Now, we come here. So, RRT pseudocode, we see that we initialize the tree T with the start node x start. We have seen that in the previous thing as well. So, this is the x initial point or x start point here. Okay. Now, for I equal to 1 to some number of iterations which we are looking for, there will be the random point sampled from the space. Then we check that which is the nearest node in T to x rand. Okay. What happens here? Now, the x new we steer from x nearest toward x rand using the step size eta. Okay. If the path from x nearest to x new is collision free, then we add x new to the tree and then add an edge from x nearest to x new. Okay. That means it becomes the path. Now, there is a criteria for goal checking, because at the end when the vehicle, say the drone, is exploring the environment, finally it should go or it should reach the goal to complete the entire mission, right. So, after that it will be checked that whether this new point is very near to the goal or not. So, we are checking it like this, where epsilon is a very small value. So, if the distance between x new and x goal is less than epsilon, then we tell that it has sufficiently reached closer to the goal, right, the goal point. So, then we see that we return the path from x start to x new, which becomes the entire path. Okay. Okay. So, once we get that, this loop will keep on running for the number of iterations which we have specified, and if no path found, then that will be returned like this. Okay. So, this is the pseudocode which we are having. We will show one example scenario here, where the drone starts from some point at the initial position, okay, in a cluttered 3D environment, but we are seeing it from the top view. It is 3D, we are seeing it from the top view. So, we know that how things are happening here. Okay. Since the drone we are expecting here to be in the particular altitude where it will be hovering on and will be moving in different spaces. So, we are representing it as a 2D waypoint, and in that way the simulation is coming here. Okay. So, the drone starts at the initial point in a cluttered environment, then RRT algorithm rapidly explores the free space. So, this space is entirely the free space. Okay. Now, the RRT rapidly explores free space by sampling random points, that is what we have seen. Then the resulting path is feasible, but often non-smooth and might be longer. That means, we can see from here this particular figure that sometimes this path have some sharp turns. So, it we can't claim that it is very smooth path, and also there can be some smaller path possible to reach this particular goal position, but still it might be the scenario that the drone which actually is taking through the RRT algorithm is a longer path. Okay. So, quick computation suitable for real time obstacle avoidance, that is there, that advantage is there, which is also an advantage against S-try algorithm, but paths may require post processing to make in order to make it smooth or to add some optimization, because as I already told that if for RRT algorithm, if the path exists, then it is guaranteed to find it out, right, but that might take infinite duration to find it out. So, the computational time might increase, but however, it actually guarantees to find out the path. Okay. So, what is the limitation of RRT? Paths are often suboptimal and not smooth. Tree commits early to the suboptimal paths because the check for optimization is not there. It struggles in complex environments like mazes or narrow corridors, something like this sometimes, where the goal is around where the goal can be reached here after you cross a narrow passage. Okay. No path improvement over time. Okay. It is sensitive to step size and sampling density, does not refine solutions with more iterations. So, if we consider only on RRT, then these problems will be coming, right. But still I would say that RRT is a very popular algorithm for autonomous vehicle navigation, and many literature have been published with the advantages which RRT provides, right. Now, we will introduce RRT star. So, when RRT star, we can say that it is an extended version of RRT, and it has certain advantages or certain features which can avoid the limitations of RRT, right. Now, what is the main limitation? The main limitation is that RRT might not get the optimal path, though it will find the path, right. So, the extension of RRT with path optimization when we do, we get the RRT star. Okay. It retains exploration benefits of RRT, but there will be certain other features like best parent selection. When a new node is added, it chooses the parent that gives it the lowest cost path. Okay. And then the important feature is that it rewires the tree nearby existing nodes through new node to reduce the path cost. So, in these two steps you can see that the main objective of RRT star is this optimization, which we were missing in RRT, right. So, in this way it will be getting one asymptotically optimal path and converges to the optimal path as the number of samples increases. Okay. Fine. So, in that way actually RRT star gives some advantage over RRT. Okay. So, asymptotic optimality, RRT is designed to converge to get optimal as the number of sample increases, that is what asymptotic means. Then it is a cost aware tree rewiring. So, this point is very important because that is the part of the optimization which the RRT star is doing extra over RRT. So, after adding a new node, RRT star checks the nearby nodes, rewires the connection to minimize cost to come, select the parent node that results in lowest path cost. So, these are the two steps, right. Now, what happens? Higher quality paths without post processing will be obtained by RRT star. It will be generally smoother and shorter compared to RRT. Okay. So, RRT star algorithm steps, we see that first it will sample a random point in space as we have seen for RRT, then it will find the nearest node in the tree to the random point, fine, then extend the tree from the nearest node toward the sample point to create a new node x new, fine. After that there will be a collision check. If the path is free, add the new node to the tree. Now, what happens? Find all nodes within a neighborhood radius of the new node, not just a single nearest node, right. Out of this it will choose the parent node of all neighbors within this radius which we are talking about, neighbor radius. It connect the new node to the one that results in the lowest cost path from the start or starting point. Okay. Then rewiring for all nodes within the neighborhood of this new node, check if the connecting if connecting them via the new node lowers the cost to come. If so, then update the parent to the new node. Okay. So, we will see that in more details in the next slide. Then it will be repeated until the goal is reached or some stopping criteria is met. Okay. Fine. So, what is here? You can see it uses a set of nearby nodes. So, this particular radius which you are, this particular circle which you are seeing here is the neighboring zone, whatever nodes are inside are the neighboring nodes. So, it connect the new node to the best cost parent, something like this which is happening here. Okay. And you can see that that will help in getting a path which is shorter than other paths, right. In that way the finally what it generates will be the shortest path in terms of distance or whatever criteria we will be fixing for it. Okay. So, the rewiring of neighbors to improve their cost is happening at this part, then the tree keeps on improving over time and balances exploration and optimization. Okay. So, that is what RRT star is happening. The random node is found and then from the nearest node to random node when we are moving, then to add the random node into the network, it actually takes care of the optimization. So, that finally when we get it, it is not suboptimal like RRT. Okay. Fine. Now, RRT star algorithm optimality, as I told, is taken care by these particular steps, that means parent selection and rewiring. RRT star iteratively improves the solutions by always connecting through lowest cost neighbor. It performs rewiring, very important, to of existing nodes to reduce path costs whenever possible. These enhancements enable RRT star to find better and maybe smoother or shorter paths with each iteration. As the number of samples increases, the solution approaches the true optimal path. Okay. So, as we are checking it for more number of iterations and the number of samples are also increasing in the environment. So, the solution approaches the true optimal path. So, what was missing in RRT? RRT used to find the feasible path. If it was present, then it was not optimizing it, we were getting a suboptimal path. We were not in a position to claim that whether this path is the shortest path or it is optimizing some objective function or not, but that is being taken care here in RRT star algorithm. Okay. So, it achieves optimality through two main mechanisms, as I have told. The one is cost aware parent selection, another is rewiring. Okay. Fine. So, together this ensure the path becomes closer to the minimum possible cost from the start to goal as the tree keeps on expanding. Okay. So, that is what RRT star is. Now, we see what is the difference between RRT and RRT star. Fine. So, you see the first point is expansion style. So, both are doing of course, they are selecting the node in a sampling based method. So, but what happens in RRT is that it is rapid and random expansion, whereas RRT star with the two major steps of pattern selection and rewiring becomes more structured with optimization steps. Fine. Now comes path quality, of course. So, it is irregular. So, there might be some sharp turn which is not good for the autonomous vehicles. There might be some violent turning required to follow the path, that will not be energy optimal, of course, and often suboptimal paths will be there. However, in RRT star it gradually improves and approaches the optimal path as the number of sample increases. So, in that way you can say that RRT star, yeah, of course, will find better place in autonomous vehicle navigation, right. Tree structure. Tree structure here is unrefined for RRT and it is minimally rewired, whereas in RRT star that is the main USP of RRT star, that it continuously rewires to minimize the cost. Convergence may not converge to the shortest path. However, in RRT star it will converge to the shortest path over time. So, this is also a problem for RRT, right. Now, usefulness for drones, it is good, RRT is good, fast and reactive planning, but RRT star is better for efficient and smooth navigation. So, it will find out shortest path, it will give you smooth or smoother path compared to RRT. Okay. Computational time faster to compute. However, here of course, RRT star slower due to rewiring and cost components. So, since the optimization part is also being played in RRT star, we know or we can just clearly understand from this particular feature is that the computational time will be a little bit more compared to RRT. Okay. So, that is where like for RRT star we have to be careful that how fast it is giving the path, whether it is in that way feasible for real time implementation or not, that we have to check, right. Now, finally, what comes here is the application fit. So, RRT can be used in time critical or one shot planning scenarios. However, when you have a bigger mission, then optimal path planning is also an objective which we cannot ignore all the time. So, optimal path planning in static or known maps can be achieved by RRT star. Okay. So, these things are very important to understand. So, first what we covered is A star. First we covered Dijkstra algorithm, then we saw there was some problems, so we came to A star. A star was giving us some kind of optimality, but again the problem was that it became memory extensive and at the same time heuristics was required, right. So, to avoid those two things, we brought up with sampling based path planning. So, the first example of sampling based path planning what we discussed here is RRT, of course. We saw that it is doing well, but it does not have the feature to find optimal path, right. So, the next phase of improvement what we find here is RRT star, which can give the optimal path by two major steps into its algorithm. One is cost effective or cost aware parent selection in the node expansion or in making the tree in that way, and at the same time it has another feature that is called rewiring, which also keeps the shortest path or optimization of that flavor in mind, so that both the steps, parent selection and then rewiring, takes care of the suboptimality problem of RRT, right. Okay. So, we can see here that there is one path which is simulated with RRT star algorithm. Again we know that this particular space is the configuration space which is available. So, the same environment start and goal positions as RRT example we are using here. RRT star incrementally rewires the tree to improve the path cost. It results in shorter and smoother path. So, if we go back and see the previous example, you will see that this path is shorter and it has less number of sharp turns. Okay. So, it becomes shorter, smoother and more optimal, requires more computation time compared to RRT. That is something which we cannot avoid directly, because RRT star with some added feature in its algorithm is giving a better path which is shorter, smoother, optimal. RRT is not doing that. So, in that way some increase in computational time is expected, but we have to be careful that whether for our application it is sufficient or not. Okay. So, this is ideal for missions where the path quality and efficiency matters. Okay. Fine. So, what theoretical guarantees we get in RRT? It is probabilistically complete. That means, if there is a path, feasible path, it will find it out, but it was not optimal. In RRT star, what we do is that it is probabilistically complete, but with two different optimization steps, it is finding the optimal path finally. One more thing is that it RRT star converges to the shortest feasible path. Okay. More number of samples, better path quality, but at the same time what will happen here, you can understand the time for computation will go up, right. So, that becomes a concern. So, there is a trade off between speed and optimality, right. So, depending on the application which we are looking for, we have to decide that which is more important for us to save. If we need more speed, then sometimes we have to drop down some optimality and we have to compromise in that way. We have to choose some suboptimal path. However, if we are very particular about getting something optimal, then we have to compromise in terms of the speed, right, or computational time. Yeah. So, how the control integration happens for RRT and RRT star algorithm? The output path will be coming from the RRT or RRT star algorithm, that is the planned path, then that comes for the trajectory generation, then some time parameterization factors will be included in the path, then if required then path smoothing or some post processing units will be there. Finally, it comes to the controller which will be say LQR, MPC or PID, something like this, which we have also like PID we have covered in this course as well. After that, there can be some safety layer where the obstacle avoidance will be taken care of in a specific way, more specific way, and of course, we need to consider the system dynamics of the drone which we are talking about. There will be state feedback to make things or to make the controller accurate, even more accurate. So, that is the control integration of RRT or RRT star, and once we get the path, it will be this particular path obtained by RRT or RRT star will be followed by the controller of the drone, and that is how we make use of it. But what are the challenges of RRT star? Yeah, we have seen that already. There is a slow convergence rate or convergence speed, then sometimes it can be highly computational cost as the number of samples increase. Then the path quality fluctuation can be there, the quality of paths during iterations may vary and sometimes fluctuate before settling to an optimal path. That also can happen sometimes, so we have to be careful. Okay. Weak environmental adaptability. RRT star can struggle in highly dynamic or rapidly changing environments because it relies on incremental improvements based on earlier samples, right. So, if the environment is changing very rapidly, then that can be a challenge for RRT star. It requires careful parameter tuning and local optimality issues also should be taken care of. Without enhancements like adaptive sampling, RRT star can suffer from local minima and suboptimal initial paths before gradual refinement. So, to in order to make the RRT star even better, there are some variants of RRT star like informed RRT star, bidirectional RRT star. The students are encouraged to go through those concepts as well, but discussion of those topics in detail is out of scope for this particular course. Okay. So, now we summarize our lecture. RRT was fast, simple, feasible path planner, and we get some advantage over A star algorithm, right. Now, RRT star tries to avoid the limitations of RRT by adding the path optimality feature over time. It is useful for high dimensional drone planning, both RRT and RRT star, because in this particular scenario we have seen that A star will face struggles because A star believes on a grid based optimization or grid based exploring of the environment, right. Now, the variants enhance, like as I told, informed RRT star, bidirectional RRT star, those enhance the practical performance even better. So, we have to choose which one we are going to use based on the application which we are looking for. Okay. So, for further reading, we would suggest this particular book by H. Joseph and some other authors, The Principles of Robot Motion, Theory, Algorithms and Implementations. It has a very nice explanation about RRT and RRT star algorithm. So, as the additional reading material, the students should look into this. Okay. There are some MATLAB resources where MATLAB MLX files are available for RRT and RRT star. I think the students can go through these particular links to find the codes and then implement. Okay. They will have much clearer understanding about this particular concepts of RRT and RRT star, and it will help them better in interpreting how these two algorithms are working. Okay. Thank you so much. See you in the next lecture.